Can you say it right?
Yes. All right, so are you ready?
Yep.
Okay, so welcome everyone. So it's my pleasure to welcome Francis Bach from INRIA and ENS. We'll be talking about information theory with kernel methods. Yeah, thank you.
Okay, so thanks a lot for inviting me. It's a pleasure to do an after dinner talk in Caltech. And so today I'm going to talk about a topic I've not talked about before. So it's very recent. This is like my Christmas vacation treat. And so it's trying to mix like a bit of kernel methods, which I've been working on for quite a while, and information theory, which I've been more like a user of in the last 20 years. So the idea today will be to study probability distributions. Okay, so I will give examples why this is important, but this is like a core task in statistics, data science, like signal processing. And what is often done is that to characterize distributions, we look at moments. So expectations of some functions. So typically in RD, you have monomials, so you get all the moments like E of x squared, and so on. But more generally, people have focused on more general features and can have finitely many if you have a Euclidean space, or infinitely many. And this is characterized by some map from your input space where your data live to some Hilbert space. If you wish, you can think of the Hilbert space being finite dimensional for quite a while. I think it's fine. And what people call the mean element is actually this expectation of phi of x under P. So this is a longer history of using this mean element for many things. So for fitting, for example, so the method of moments, okay, I don't know how old it is, but it's very, very classical. You compute moments from the data, and then you try to find some distribution with the same moments. And a key aspect is that if you take sufficiently many moments, then you're going to characterize everything perfectly. And there is this nice area in kernel methods where if you take a Hilbert space, and I will define everything like in a moment, then you can fully characterize your distribution. So the mapping from P to the mean element is injective. So whatever you can do on the mean element, this tells you something about the distribution. And this also gives you a natural metric on distributions by computing the square distance or the distance in the Hilbert space between the mean elements. So the good aspect of this is that this can be estimated quite easily with given some samples of P and Q. And typically the rate of convergence in terms of number of observations is parametric. So it's 1/√n. So although you have to do you want to fully characterize the distance between distributions, you still have some parametric rates. And the extra other benefit is that the feature map only enter the equation through the kernel K of xy, okay, which is dot product. And in many cases, it's hard to compute phi of x, but the kernel can be easily computed. So this has many applications. Okay, a nice review paper by Muande and colleagues. And this is, of course, often done in model fitting, which I've mentioned already. But you can use those like distances between distribution for independent tests. It's often used for like generative networks in the deep learning. So there are many applications. So here, as you may expect from the start, the talk will be mostly on the methods part and not so much on the application parts. The goal of today is all of this line of work is great, but there are other ways of doing similar things, which is information theory and with various like divergences, either a link. And the goal of the talk is to make a more formal link between what you can do with kernels and what people often do in information theory. So for this, I will need to put some structure in the feature map. So not take any feature map, but take feature maps which are essentially rank 1 matrices or rank 1 operators. So I'm going to consider one feature map phi of x and consider the mean element, but for the phi of x times phi of x transpose. So if phi of x has finitely many dimensions, this corresponds just to the if it has dimension d, this is a d by d matrix, a rank 1 d by d matrix. But if you go to like infinite dimensions, you get an operator from edge to edge, okay, which is represented as the expectation of the tensor product between phi of x and itself. Right, so from the start, this operator is symmetric, self-adjoint in a thin dimension, and it's positive semi-definite, which I will mention PSD because you average rank 1 PSD operators. The main tool we're going to consider is to look at not at the L2 metric between mu p and mu p and mu q, but at the specific form of quantities which come from quantum mechanics and the von Neumann entropy and the relative entropy. And by using this, we'll reach interesting properties. First, a clear relationship with regular information theory, and I'll be very precise in this. You can still do some estimation in 1/√n, a nice benefit from the what we had before with the mean element. You can also do various things regarding like multivariate modeling if you have more than one distribution, and also variational inference. And I'll go rather quickly on the last two aspects, so I want to focus more on the first 2 points. All right, so let's get down to it. So I'm going to consider covariance operators, and again, for simplicity, if you prefer, you can consider that phi of x is finite dimensional, and this is just a covariance matrix, or the non-centered covariance matrix. So we'll start with an assumption on the kernel. We're going to assume that we have a positive definite kernel on our input set. And again, here, x can be anything. So I'm going often to take the hypercube as a motivating example, or the Boolean hypercube as well. But it can be any set, and I'll come back to that in the conclusion. So I'm going to assume the set is compact, and that the kernel is a symmetric function, which is positive definite, which means that if you take all matrices of pairwise evaluations, then that matrix is a PSD matrix. So I'm going to assume that k of x is less than 1. And from that, it's it's a classical in machine learning and statistics to define a space of functions, which is essentially the span of all functions where you fix a point x and you leave the argument open. Okay, so it's y gives k of xy, the function it's a function, and by taking the span of that function with the proper metric, you end up with a nice, well-defined function space. And to relay the function space to the kernel, you make sure that that single bump, when it is like the dot product with another bump, ends up being exactly the kernel. Okay, so this is a classical reproducing property. And so this is the somewhat formal way of seeing those function spaces. What people often do instead is that you know that for any kernel which is PSD, there exists a phi, okay, and a map. There exists a phi, which is a map between the input space and some Hilbert space for which k of xy is a dot product. And then you consider the space of functions defined as linear functions of that feature space. Okay, so this is the equivalent notion. Either you see first features and linear functions of the features. Okay, this is one version, or you see directly the Hilbert space of functions. It doesn't really matter. At the end, our function space is space of linear functions in the feature map phi of x. We're going to assume that that feature map, that the kernel is said universal. So essentially, this space of function happens to be dense in any reasonable subset. Okay, and we need to be dense in the set of continuous functions. Okay, with the proper norm. And in RD, this is many kernels satisfy that that property, like the Gaussian kernel will satisfy it, and this corresponds to infinitely differentiable functions. But any sublet space with a sufficiently high order will also satisfy those conditions. Of course, to get less differentiability. The polynomial kernel does not satisfy those assumptions. So this is the classical thing. So here, know that phi of x will sometimes be explicit or sometimes be only implicit defined through the kernel. Okay? You know there exists some phi of x, but you will actually never build it. So this is a covariance operator, which is a classical tool in statistics. And it has some properties. So it is, as I've mentioned, PSD. If you assume that the norm phi of x is always less than 1 and the trace is less than 1, so overall you get a unit, something which is a trace class, so trace is less than 1. So it has a sequence of decaying eigenvalues tending to 0. And again, if you assume the map, the kernel is universal, you get an injective map. So essentially, this is a very specific min element for a particular feature which is this one, and it's also injective. So examples, so if you take the torus, so this is just like the hypercube with like periodic boundary conditions, okay, then you are a kernel. If you take a kernel which is like a function which is a translation invariant dependent only on x minus y, where q is one periodic, then you can show that you get a positive definite kernel if only if the Fourier series is non-negative. And so now with this, you can get an explicit feature map, which is an infinite dimensional feature map, which is indexed by the integer lattice, and you get all like Fourier features. Okay, and a classical example in this respect is to have this exponentially decaying function. So I'm not giving you the formula for Q, but the formula for Q as well. But as I've mentioned, the kernel framework is not only focused on RD or on the vector spaces. You can also apply it to finite sets. And I will use a bit later the finite sets for which are classical kernels. So the obvious one is what is called the orthonormal embedding, where phi of x and phi of y are either 0 or 1, depending if x is equal to y. It's often called the one-hot encoding of discrete variables. But I'm also going to consider toward the end the Boolean hypercube, where now phi of x will not be, so phi of x, of course, to get the orthonormal embedding, the size of phi of x, dimension has to be at least the number of elements, but you can reduce phi of x by taking just monomials or just x or x squared. Just to give you examples of what we may consider here. So now let's move to the quantum part. So this is the, so I'm not an expert in quantum theory. I took a class when I was at École Polytechnique, but I have to say I totally forgot. I found my book back, and the book mentions indeed the negative entropy. And this is defined for any PSD operator as the sum of lambda log lambda when lambda goes over all the eigenvalues of A. Okay, so you can think of if you have a finite dimensional Hilbert space, then this is a finite sum, but otherwise you have to, of course, to make sure that the sum is summable. Okay, so it's a spectral function because the function that lambda log lambda is convex. This is a spectral, this is a convex spectral function. So this is a convex function. And as any convex function, you can build the Bregman divergence for that convex function, which is just the function at A minus the function at B. I'm not sure this is a Bregman. This is the Bregman. The function at A minus the function at B minus the gradient, okay, times the variation. So it's the difference between the tangent of the function, and you get the relative entropy, and which is related to the KL divergence, okay, in you look similarly in the information theory. So here the key that from the start, like all Bregman divergences, this is convex in A, okay, but it turns out that, and those properties are used a lot throughout quantum mechanics or quantum information theory. You know much more, you know many more things. The first one is the consequence of being a Bregman divergence. This is that it's non-negative and equal to 0 if only A equals B. Okay, so this is like not very complicated, but it happens to be jointly convex, and that joint convexity is really what makes it what is important. Okay, for the later developments. So I will not explain why precisely, but I'm going to use it. I'm going to use it directly. And this is known. There are other properties which I will not really focus on too much today, which is like related to what people call the operator Jensen inequality or the quantum measurements. So you have other inequalities if you apply other operations. Okay, so if here, so in quantum mechanics, if you have a set of matrices which satisfy this, then this defines some form of quantum operation that preserves something, and then for that, the information tends to decay, okay, when you apply the operation. Okay, it's often called the monotonicity of quantum measurement. I'm going to briefly use it later in the talk. And I don't know if Joel is here or not, but those tools like this quantum relative entropy and von Neumann entropy is used a lot to prove matrix concentration inequalities. And here Joel is the expert here. I'm not going to use it, but I just want to mention that that tool is being used in other places. All right, so now let's define what I mean by the kernel entropy. So you're going to apply that relative entropy to the covariance operator. So they give me P and Q, compute sigma P and sigma Q, and compute the von Neumann relative entropy. And boom, you get what I call the kernel relative entropy. So a few properties. So it's finite with some simple properties regarding the density of P with respect to Q. They are like weaker statements. This is just a simple statement. By definition, at most, it's non-negative. It's a Riemann divergence, and it's equal if only sigma P equals sigma Q. And if you assume the kernel is universal, since sigma P is characterizing P, then this is equal if only P equal to Q. Okay, so this is a good notion of divergence. And almost by construction, it's jointly convex in P and Q. Why? Because D is convex in sigma P, sigma Q. Sigma P is linear in P, sigma Q is linear in Q, so you get joint convexity. And this is often a good property of entropy. Then you can also build a notion of non-relative entropy, classical entropy. But I don't want to go into the details here, but this, you have to be careful with the normalization constant. And I want to avoid that at the moment. And at the end, one thing you may ask yourself is what is the exact difference with entropy? Okay, because if I start to prove too many properties of that new notion of entropy, then because of the various axiomatic definition of entropy, I will get the entropy. Okay, so essentially, I'm going to miss one property which makes it different from the entropy, which is the conditioning thing, which I will explain at the end. But we don't get the entropy, we miss some of the properties. We preserve convexity and things like this, but we don't preserve everything. And it has to be the case, otherwise we get back the entropy. All right, so just to get the intuition going, what's happening for a finite set? If you have an orthonormal embedding, then you can show that all those covariance operators, which are covariance matrices, are all can be diagonalized in the same basis. Okay, so you can simply like take rotate your space so that phi of x is just a canonical basis vector, and then all covariance matrices are diagonal matrices. And this means that when you take this, you're going to sum over all the eigenvalues, and you're going to obtain like the sum over all eigenvalues. So this is all the probability mass values, okay, for over all elements of X, and you end up exactly with the Kullback-Leibler divergence. So this is, at least for finite sets, where I cover exactly the shell entropy. So this relationship is well known in the quantum mechanics. Okay, that's not a new thing. The question is, can you go beyond finite sets? So this is what maybe there are two technical slides in this talk, but I wanted to put them because this is where the action is. So this is going to show that whatever the kernel is, okay, as long as you get this upper bound, okay, so you need to define a notion of scale, okay, and here the scale is 1. Then the new kernel relative entropy is less than the classical relative entropy, the Shannon one. And the proof is 4 lines, okay, so you first express this sigma p as itself, okay, and sigma q as the integral over dp, okay, of the same quantity, but now you introduce the density of q with respect to p. Okay, so now what you have the function d of the integral of a quantity over p, an integral over another quantity over p. Since d is jointly convex, you can use Jensen's inequality and take the integral over p of x of the distance between what's here and what's here. Okay, and so what's here you get that, and what's here you get this. Okay, so this is just Jensen's inequality. And now what you have here you have a rank 1 matrix, well, rank 1 operator. Here, a rank 1 operator with exactly the same like low rank So the same eigenvector. Okay, so it has an eigenvector along phi of x, and this is the same one. And this means that you can compute this entropy directly by computing all eigenvalues. Only one is non-zero, the rest is zero, and the zero leads to zero because it's zero here. And you end up with exactly this quantity. And then you refactorize it, and you use the fact that phi of x is less than 1, and boom, you get to your relative entropy. Okay, so with direct application of James's inequality, you get a lower bound on entropy. Of course, the question is, how tight is it? Okay, because lower bounds, you can always get 0, it's a lower bound, okay, so it's not very useful. And for that, I'm going to define a special operator, which is the covariance operator for the uniform distribution. Okay, so here I've assumed compactness, so I can define the uniform distribution, and sigma will be the corresponding covariance operator. So to get the other direction, this is where I will need to use a bit of quantum mechanics or a bit of properties from which is used a lot in quantum mechanics. So let's have a look. And in quantum mechanics, there is often like you can do measurements, okay? And there are often doing measurements corresponds to taking traces of your density operator. So here sigma p will be representing your quantum state, and taking trace of a matrix D times that operator will be some form of measurements. Okay, and so I'm going to define measurements for all possible elements, which will be a PSD operator, okay, where you take the rank 1 matrix and which you renormalize by sigma. And this renormalization is made so that the integral of D is exactly identity. Why? Because if I take the integral of D here, I get the integral of that, which is exactly sigma. And since I normalize, I get back identity. Okay. So now I can take those measurements, okay, for all dy, and it's known that if you take measurements which are PSD matrices which sum to 1, you call that the measurement p tilde of y, then you have that the classical KL divergence between p tilde and q tilde, if you take two distributions, will be less than the original relative entropy. So this will be this inequality. This inequality will be just the monotonicity of quantum measurements. Whenever you measure, you reduce information. Okay, this is similar to regular information theory. So here the difficulty is that what is a measurement? So this is you need to have a specific assumption being satisfied, and this is one of them. Now you can look at what P of y is related to P, and so by definition, the trace of dy sigma P is exactly you take trace of this times sigma P. Sigma P is the integral of phi of x times phi of x transpose, and you end up with a square like this of phi of x transpose phi of y, but renormalized by the inverse, by the square root of the inverse of sigma. So you get a square. So at the end, you get that P tilde of y can be seen as essentially a smoothing of P of x. So you take the integral of what the smoothing kernel, and which is classical in statistics. So a smoothing kernel, typically, this is something which is non-negative and sums to 1 when you integrate over one variable. It turns out that this is exactly what we have. It's non-negative because you have a square, and it does sum to 1. Okay, so this shows that for a lower bound on our new quantity, it's not P and Q, it's a smooth version of P and Q. And you end up with what I call a sandwich result, where our new quantity is between the regular Shannon relative entropy and the Shannon entropy of the smooth versions. Okay, so for the experts, that inequality between D of PT, QT, and this one is just the data processing inequality, and we just have been able to sandwich something in between, which is this one. All right, so now we have a sandwich, and with that sandwich, you can essentially measure the distance between this one and this one. Why? Because it is simply like measuring the distance between entropy and entropy of the smooth version, and this can be done explicitly. And here I'm going to refer you to the paper for the exact specifics, but you can show that the distance between the two is non-negative from what I've seen before, but is upper-bounded by a quantity that depends only on P and Q and the how wide is the smoothing kernel. Okay, so if the smoothing kernel is a Dirac, then this would be 0, and if it's more than further away from a Dirac, then you get further away from 0. And what you can show is that for my torus example, okay, which is one of the motivations for this work, then if you have a bandwidth parameter, then you can show that there's a big O. In the big O, there are like many constants that may be exponential in dimension, but the dependence on the sigma, on the bandwidth, is only square. Okay, so this is like this is directly obtained from that. Okay, so here what we see is that in those examples, as you get like a smaller and smaller bandwidth, you get closer and closer to the true entropy. All right, Oku, feel free to interrupt with questions. So I forgot to mention, but if you have questions at this time, don't hesitate to ask, or we can take them at the end if you prefer. So just like speak and I'll stop. All right, so now we have we have like both upper bound and lower bounds, and now let's try to see if we can do things with it, because at the moment I have defined my entropy as something like that, where I need to compute covariance operators, which are objects in infinite dimensions. So maybe it's all nice on paper, but can you use it in practice? Okay, and this is where we're going to leverage classical kernel methods. So let's try to see. So there are several ways of accessing your distribution. I will present 2 ways, and mostly one, which is if you have some sample. So you have NID observations, x1, xn, and you want to see if you can compute the distance, and here's the distance to the uniform distribution. Okay, so now I can compute this distance between like sigma p and sigma is the uniform distribution, which you assume like simple enough. And when you expand, you have various terms which are reasonably easy because they are linear in your sigma, and there is this trace of sigma p log sigma p. So what I will focus on now is, can I compute this in a polynomial time if sigma p is known only through n sample? So there is more natural estimator, which you can directly think of, is replace sigma p by the empirical covariance matrix, or here covariance operator, which is defined here. So you sum over all the data, the rank 1 operators. And it turns out that this is enough. And there is first, you need to make sure that this can be computed. Okay, and so why can this be computed? But this is the traditional kernel trick. Essentially, the eigenvalues of sigma p hat are the same as the eigenvalues of the kernel matrix divided by n. So this is used, for example, in kernel PCA. Okay, and so this is a very classical. This is what I was doing during my PhD, looking at kernel matrices and things like this. So we can leverage the same techniques. So sigma p hat is a finite rank operator, and so you can compute its eigenvalues by having the eigenvalues of k. And since this function is a spectral function, you can just do the same spectral function on k over n. So it can be computed. It takes n cube in the worst case, but there are ways of, so we can here leverage 20 years of kernel methods to reduce the complexity. Okay, I will not mention it today, but n cube, okay, at least from the first perspective, it's enough for me. Then you can compute it, and how does it work? And so here you can have a very precise upper bound, and that upper bound relies on quantities which are often used in the analysis of kernel methods. And for the experts in kernel methods, they recognize here the leverage scores. Okay, so the squared leverage scores, and this is typically the analysis of kernel methods, often called the maximal degrees of freedom. And if you can bound this, okay, and here the subtlety is to bound the integral over all regularization parameters. Okay, if this is bounded, and if you assume like lower bound on the density, okay, then you get an explicit bound on the L1 error between the estimate and the true one. It's explicit, okay, with explicit constants, and the key aspect is this one, okay, that you get a 1 over root n behavior, which is somewhat to be expected. from kernel methods, and you get a constant, and which depends on the degrees of freedom, which is also to be expected, and plus some logarithmic terms. So here what surprised me is the absence of regularization. Okay, so you don't need to control for the eigenvalues going to 0, okay, which is typically the case. Don't like to have lambda being too close to 0, but here it's fine. Then let's look at some examples. Okay, and so for this to be finite, you need the eigenvalues of sigma to decrease sufficiently fast. So typically exponential is enough, but any polynomial of degree like 1 over k cube will be enough. And if you take the torus example, you can compute C explicitly. Okay, and you get C being like a dependence on dimension now, strong. And by putting sigma over there, you get this rate of convergence. And now, and this was a bit unexpected from the whole like goal of the work is now we know that essentially we know that this quantity is away from the entropy with error sigma square. We know you can estimate this quantity with error this. So by finding the good sigma, we get a new estimator for entropy. Okay, and if you do the math for the optimal value of sigma, you end up an entropy estimation in constants, and those constants again depend exponentially in dimension potentially, but the rate is now something which is of that form, and it's not optimal, but it's not too far. Okay, so the optimal entropy estimation is a nice paper by Han and colleagues with the same regularity. So here just Lipschitz continuity it's better, of course, but we're not so far off, and I think it was kind of interesting that it's a really indirect way to estimate entropy, but it does first. It has some nice properties. It preserves some convexity properties, and the rate is not too bad. Right. One example, just to highlight the fact that you can run this. So this is in 1D for simplicity, and I've taken like some distribution. I forgot which one, for which the entropy can be computed exactly over there. This is a differential entropy, and I'm finding two different bandwidths, and n is increasing. And we know that as n increase, you converge to the true Kernel entropy, which is what's happening on the right. And as sigma goes to 0, you get closer and closer to the true entropy. And this is what you get is that you converge each curve when n goes to infinity, they converge to their limit, and the limit gets closer and closer to the true entropy. So there are a few things that to notice here. You're always below. It's normal. Okay, we have upper bounds here. Okay, so you better be below at the end. And it always goes down, and it's simply a consequence of Jensen's inequality, because the expectation of this is convex, is bigger than the value at the expectation. And since sigma p hat is an unbiased estimator of sigma p, then you get this that in expectation you're always above. Okay, the fact that those curves are above their limit, in a sense, it's normal. Right, so this is if you know the distributions through samples, but if you know something a bit different, like some moments, okay, you can be much faster, even exponential, but you need to access your density with different oracles, like expectation of kernel matrices. Right, so this is the main property you can estimate it. Now let's look at other properties that are typically related to entropies and see if we can play the same game with our new notion of entropy. So first game is entropies are used a lot to characterize dependencies between distributions. So if I have two random variables living in two spaces, x1 and x2, I can try to see if I can characterize dependence between x1 and x2. And so I'm going to consider the product set, okay, it's classical, and what had been done before a lot in kernel methods is to consider the concatenation of the feature spaces. Okay, so if H1 had dimension D1 and H2 had dimension D2, you will consider a D1 plus D2 a space of dimension D1 plus D2. Here, which is just the product. But you really need to take the tensor product of dimension D1 times D2. And this corresponds to the tensor product of the two feature maps. And this defines now covariance operators on that space if you take the joint distribution. But you can also consider the covariance operator for the marginal distributions, each defined on their own space. Okay, so this is the key here, that you're not going for D1 plus D2, but D1 times D2. And in earlier work, during my PhD, we were doing more the D1 plus D2 kind of thing, and we are not able to characterize things correctly. Here we can, because we take the full tensor product. So first thing, a classical thing, you can define the mutual information, which is the KL between the joint distribution and the product of the independent distribution of the product of marginals. And this corresponds to taking the kernel entropy between, the quantum entropy between the joint and the tensor product of the marginal operators. And it turns out that this is non-negative mobile construction, and this is characterizing independence. So this is 0 if only if x1 and x2 are independent. This extends to more than 2. Okay, and this was not true if you take the concatenation and not the tensor product. This is true now. This is more a nice property. Where things fall apart, okay, is if you want to characterize conditional independence. Okay, so you can play similar things. Okay, so you have this, I forgot the name, but you can characterize conditional independence through entropies of triplets. Okay, so x1 and x2 are independent given x3 if a certain relationship between entropies is satisfied, because of joint entropies. And here it's not anymore a characterization. It's only like one direction works, not the other one. And another important property, which is used a lot in quantum mechanics, is the data processing inequality. If you marginalize, you reduce the information. And this is where things fall apart. This is precisely where things fall apart, is that in regular information theory, you get equality here if only if the conditional of there's a mistake here. Okay, it should be q of x1. Okay, here. So here you get equality if only if the conditional of x2 given x1 are the same for p and q. This is why you get equality. And here this is not true anymore. Okay, so this is where things fall apart, and this is why we don't get exactly the entropy. We cannot do conditioning correctly. All right, so other things that you can play with entropy, and people do this a lot in machine learning, is to play with like log partition functions, which are simply the Fenchel Legendre conjugate of the relative entropy. What I mean by that is, if you want to compute a log sum x function, so the expectation by the integral of the exponential of any function f with respect to some dq, think of dq as being the uniform distribution on x, then you can see it as a suprema over a linear function of a measure p, okay, and f, and minus the relative entropy. So these are the classical properties of convex duality between like entropy and log partition function. And this is used a lot in as an inner loop. Computing this or approximating this is used a lot for many inference tasks. Okay, just computing is important. If you do, like, for example, if you want to estimate the marginal likelihood in Bayesian inference, you want to compute that, but you may want to use it to optimize it to get various information about for probabilistic inference. Nice book by the master, okay, and Wainwright and Jordan. And here, since we have an upper bound on this, you should expect that we get a bound also on the log partition function. And this is what's happening. So I'm going to assume unit norm features so that my relative entropy is less than the classical relative entropy. And now I get an upper bound on this quantity by replacing this by a lower bound and taking this being a bigger space. Okay, here I'll go from probability measures, which are like essentially positive densities which sum to 1, with only densities which may not be positive. Okay, so I'm leaving the positive. There's a p here. Sorry, I'm leaving. There's a p there and a p there. Okay, I'm leaving the positivity aspect being taken care of by the Riemann divergence, which will impose that sigma is non-negative as an operator, which is for which a sufficient condition is that P is positive, but it's only sufficient. And what you can notice here is that if F is itself a quadratic form, then you get everything expressed in terms of operators. And now you may start to see the fact that this can be computed if you know how to characterize a set of potential covariance operators. And this can be done approximately using semi-definite programming. If you want to know more, you can look at the paper. There is some worked out example for doing this. And one example where it's possible to be done, if you take, again, very simple example in 1D, just to illustrate that those bounds can be computed and indeed end up converging. So of course, if the entropy is converging, if you get more frequencies, then the log partition function should also converge if you use more frequencies. And here I'm taking just 0, 1, a particular f, very simple, for which you can get the log partition function as a specific number. And I'm taking a very basic feature space with frequency like Fourier components with bounded like between -r and r. And as I get more frequency components, I get an upper bound which is tighter and tighter. Okay, and this is it's always above here. I always get upper bounds. And as I take the bandwidth being smaller and smaller, I get to points which are smaller and smaller. So as you get both r big and sigma small, you're supposed to get the exact partition function, which you obtain here by solving a semi-definite problem. All right, maybe like 2 last slides. I think this one is, so I gave a talk maybe 1 year ago, probably, on optimization. And in fact, there is some direct link. And essentially, this is essentially what I've presented like 1 year ago on sum of squares optimization, but with a probabilistic twist. Okay, and the twist is by adding some temperature to make the link. So I'm going to add some temperature epsilon. Okay, just take the exact same Fenchel conjugate, but adding some epsilon. Okay, so this is the effect is known that you obtain like a somewhat perspective type behavior when you can take convex duality and you obtain a log sum x, okay, classically with matrices. And because you optimize over measures like integral over x, then you end up with, when you optimize over p, you end up with a constraint that you get that your function f has to be equal to some quadratic form in the phi of x. And now if you let epsilon go to 0, okay, 0 temperature limit, that log sum x will tend to the max. And in this spectral context, you get the lambda max. Okay, so when epsilon goes to 0, you converge to the infimum of the largest eigenvalue, such that this is true. And now you can play some tricks because you're going to assume phi of x as unit norm. And by playing around with the lambda max, you end up by exactly getting the formulation of optimization that we had worked on, which is finding a constant c so that f of x is c minus something non-negative. So it's the classical relaxation of using sum of squares for optimization, which we use for with infinite dimensional kernels. So I just mentioned it because there is really a link between those two, and you end up working with quadratic forms in infinite dimensions. So we reuse some of the tools that we have been using with Alessandro Rudi and Ulysse. Last thing, I think this is a surprise. Okay, so I was not expecting this when I started to work on this, is that our kernel entropy, they depend on the kernel matrix, on the kernel. If you change phi, you change the value. Okay, and since you have always lower bounds, you're tempted to maximize the lower bound. Okay, this is what we learn. This is what I learned at Berkeley. You try to maximize lower bound. And it's much better if you maximize like concave functions. Okay, and it turns out that this kernel entropy is a concave function of the kernel matrix. Okay, so the proof is using like operator Jensen's inequality. So this is really using a lot what the properties of the von Neumann entropy, and I won't do it now. And in fact, I wanted to prove it was convex, okay? Because if you look, it looks convex, but in fact it's concave, okay? So by proving it was convex, I proved it was concave, and I realized it like by doing simulations that I had mistaken one inequality. So always do simulations to find your mistakes. And so since it is concave, you can try to maximize. And the idea here would be to, if you do some feature map, you're going to parameterize your kernel through a PSD matrix. Yes. So since you want to preserve this unit norm bound, you're going to maximize only over PSD matrices so that you preserve this unit norm bound, and then you maximize this quantity. And this quantity is concave in lambda, not trivial, and yeah, so it's concave in lambda. Okay, so the proof is classical if you know about quantum information theory, but it's not that obvious. And you can maximize it, and this gives you an improved bound on entropy. And just to show that it can be done, then this is essentially very similar to what I had before with various values of sigma. Okay, so I take Fourier features, I take fixed decay of the Fourier coefficients, or I learn it. Okay, and by learning, I do a bit better. It's not immensely better in green, but it's better. And you end up learning like a profile of our frequencies. So this is the optimal kernel. So this is just to highlight the fact that there are algorithms to maximize the lower bound. Similarly, you can minimize the upper bound on log partition function, which we do in the paper. In fact, we do it here. So we can optimize bound for log partition functions. Okay, so here we take the binary hypercube. And we take like a phi of x, which is like affine functions. So the quadratic forms are all quadratic forms. And this is a classical modeling of this Markov random fields at the end that you're doing here. And you want to compute log partition function for those Markov random fields. And here we maximize over the eta here, the Gödel matrix, which happens to be the simplex if you want to preserve the bounds, the unit feature bound. And we compare to a bound by Jordan and Wainwright, which rely on the log determinant, whereas we rely on the not the sum of the logs of eigenvalues, which is the log det, but the sum of lambda log lambda, when lambda is an eigenvalue. And as you can see, so this is like the log det, okay, and we do a bit better if you take directly the quantum thing with eta being constant, and you do a bit better if you optimize, okay, over the matrix. So just to highlight the fact that we can get some improvements, okay, it's by far not the end of the story, but this is just to highlight that we can get like not only work on continuous distribution, but on any distribution. Now let me conclude. So the idea of the work was to essentially look at what's happening if you take the quantum entropies on covariance operators, and at the end you obtain quantities which can be estimated, but are directly related with the regular entropy. So this allows various applications in a variational inference. So some extensions, and this was for me the motivating factor for all kernel methods, is that you can apply this to all data types for which you have good kernels, okay? And all data types on which you have universal kernels, okay? Kernels where you have like a lot of features and you know how to compute the kernel. So this applies to many objects, like discrete objects, non-discrete objects. And so there are a lot of work, but not so much anymore, but there was a lot of work on this, like when I was doing my PhD and after, and this, so now you can, with those tools, you could potentially apply like information theory to at least estimate various elements, various distributions and entropies on those data as well. If you don't like KL divergence, okay, this work extends almost word for word, not the estimation part, but it's not sure about the estimation part, but it's almost sure, okay. But in terms of the upper bound, it extends directly to all F divergences. So this is the sum not of P log P over Q, but the sum of Q times the function of P over Q, and the function being convex, okay? And this is, KL is recovered with F being X lambda log lambda, but you can define F divergences with any convex F, and you recover, of course, Kubat-Leiber, you recover Hellinger, you recover chi-square, and so on. And it turns out that all the developments that have been presenting are true if you use F being operator convex. So it's one notion of operator convexity, and all of those are operator convex. So if you want to get upper bounds or lower bounds on those distances, then what I've presented applies as well. The algorithms, maybe not, because we rely a lot on the logarithm for the algorithms, but you can imagine extensions. And to finish, the references for that work. So there's an archive paper from this year, and I wrote a blog post last month. And on this, I will thank you for your attention.
All right, thank you very much. Thank you. Any questions, comments?
Francis, nice talk. One comment.
Mm-hmm.
There is a connection between this relative entropy between dense kernel matrices or symmetric positive definite or matrices or operators and the Vacchia approximation that you see being used in special statistics.
In the what? In
special statistics, the Vacchia approximation.
Can you spell this? Vacchia?
Vacchia, yes. Where you try to essentially approximate the precision matrix of a symmetric positive definite matrix.
Okay.
By products of Cholesky factors with some constraint. And in fact, if you minimize that KL type of divergence that you had on symmetric positive definite matrices, you recover the Vacchia approximation in spatial statistics.
Impressive, you know. This is what this was my hope in giving a talk, is to get like good links like that. And unfortunately, I don't get. I'm not at the office. I don't have any pen. But Vacchia.
Yes, Vacchia.
Okay, good. And so the goal is to approximate things products. Okay. And
the
so
precision matrix. So if you want to optimally approximate the precision matrix, the special statistics community that have been using the Vacchia approximation, and it turns out that this thing is optimal with respect to that quantity that you were defining. In fact, what you are defining is the KL divergence between Gaussian distributions, if those Gaussian distributions are defined by the symmetric positive definite matrices that you were you introduced in the formula.
It's not exactly okay. Maybe I think what if you have Gaussian distributions,
yes,
you obtain the trace of log of sigma p over sigma q minus the trace of sigma p over sigma q. So this is not the KL between the Gaussians. It's not exactly this.
Okay.
But I look at the Vacchia approximation.
Mm-hmm.
Other questions or comments? So maybe like a question like about like kernel learning. What you are? I mean, do you think that this would provide like a different approach to kernel learning for different questions, whether for regression or maximum mean discrepancy?
I don't know. I think it's clearly this provides a way to learn the kernel. It provides a principal way to learn the kernel for things which were not really possible before, because if you use MMD, there is no criterion to minimize. Okay, so if you use this, if you let the first slide up, if you take this, you can also, so the square of this is in fact linear in the kernel, so even better. Okay, you can optimize it, but there is no criterion. Since here we have lower bounds on a quantity that we respect, that we hope to approximate, you can maximize it. Okay, so at least you know that it does. If your goal is to approach true entropy, it will do better. Okay, so it's one version. It's one possibility for kernel learning. On those, there is no real criterion. So I have not really studied that, but this is also true, I think, for those quantities that the Hellinger distance and so on. So there are many areas of statistics or information theory or signal processing where you really want to focus and estimate on one of those. And the kernel learning aspect, it's it is also convex. It's also concave for all of those. Okay, so for the experts in operator convexity, you just need that f to be operator convex. So you have an expansion of f as an integral of a very special function, and this one is okay. Hence, all the integrals and all of those work. So the concavity is preserved. So no, you can apply this for any type of f divergence.
Okay, all right, thank you. Yeah. Other questions or comments?
Francis, I had a quick question.
Mm-hmm. Right.
So the slide on the, if you go to the slide when you found the bond 1/√n for the empirical, yeah, that one. So your example had a, with the dimension, if you go down more. Mm-hmm. Yeah. So the next one, before a slide, the slide before. So this example had the entropy estimation, now has a curse of dimensionality factor, right?
It does. I think if you, so here,
because the bound that you show on top, there is no dimension there, and below there is dimension.
Yeah, but you mean the sigma square? So at the end,
the entropy estimation, yeah. So the entropy estimation, as dimension goes to infinity, then you essentially it's very bad, right?
It is very bad. So here, the very bad aspect is on this result. So the sigma square. So the distance between trace of sigma p log p and the true entropy is of order sigma square. So it looks like there's no curse, but when you use the approximation error goes to 0 independently of dimension. Okay, but this happens also if you do a kernel density estimation. The bias part is sigma square, and the variance part is the one that explodes in 1/√10, but times an exploding constant is the bandwidth. And when you optimize the bandwidth, so if you take sigma square plus this and optimize over sigma, you get sigma, which will get like going to 0 very slowly, and you get the curse of dimensionality, which is because we don't assume any form of smoothness on P and Q. So if you assume that your density are smoother than simply Lipschitz continuous, then you can probably replace this by m over d, where m is the number of derivatives. Okay, so this is my goal is not to estimate true entropy. Okay, so but if it's just to relate to existing techniques that are whose goal are to estimate entropy. I think here it's not made for estimating entropy, but I think what I find kind of amusing is that so you take a kernel matrix from data, you compute that trace, and plus some extra constants, you get an estimate of entropy. And I think this to me was a bit surprising because I've been playing around with eigenvalues of kernel matrices for quite a while, and I had never thought of computing this and relating this to entropy. So it's just more like curiosity-driven result where I'm not sure it's going to be useful for anyone. That one, but that one, okay, that one is just like to relate to existing work, but the fact that you can estimate is important. Okay, that result is a bit important because if you take MMD, what has made MMD popular a bit is the existence of such a result. Okay, and so the availability to estimate it with a reasonable amount of data. So of course you have a price to pay that you're not going to see too much like small scale differences with MMD or with this. You cannot have an estimation rate in 1/√n and look at fine details. Okay, there's a price to pay. And yeah.
Okay, thanks.
Well, thank you. Final comments or questions? All right, it seems that there are no further questions. Yeah, thank you again, Francis, for the nice talk.
Oh, thank you for the invitation, and have all a good afternoon.
Yeah, thank you. Have a good night. Thank you. Yeah.
Thank you.
Thanks. Bye-bye, everyone. Thanks.